The universe was born in a silent, explosive instant, but that silence was an illusion. The fabric of reality itself rang like a bell, creating the very first ripples in space-time. These are primordial gravitational waves, cosmic echoes from the moment of creation. By the end of this journey, you will understand 30 distinct theories that try to explain these ancient whispers. We will explore if our universe bounced from a previous collapse, if it was born from a collision of higher dimensions, and if these ripples hold the secret to dark matter. Each theory is a different key to the same profound lock. What do you think it means to hear the sound of the beginning? The very first heartbeat of the cosmos was not a steady pulse, but a frantic, exponential sprint. This is the theory of cosmic inflation, the leading idea for what happened in that first unimaginably tiny fraction of a second. Picture the universe smaller than a single atom, and then, in a span of time so brief it defies human comprehension, it ballooned to a size larger than our entire observable cosmos. This was not an explosion into space, but an explosion of space itself, stretching the fabric of reality faster than the speed of light. The physicist Alan Guth first proposed this radical idea to solve several profound puzzles about our universe, like why it looks so smooth and flat in every direction we look. The theory suggests that all the structure we see today, every galaxy and star, grew from microscopic quantum fluctuations that were stretched to cosmic proportions during this inflationary burst. But this violent stretching did more than just seed galaxies. It violently shook the very fabric of space-time. Think of space as a vast, still pond. Inflation would be like someone grabbing the edges of that pond and yanking them apart with incredible force. The surface would not remain smooth. It would churn and roil, creating powerful waves that propagate outward. Those waves are the primordial gravitational waves. Their specific pattern, a unique fingerprint imprinted on the oldest light in the universe, is considered the ultimate smoking gun for inflation. Finding that fingerprint would be like hearing the echo of that first explosive heartbeat, confirming that our universe began not with a simple bang, but with a breathtaking inflationary sprint. But what if the Big Bang was not the absolute beginning? The theory of the Big Bounce offers a radically different origin story, one where our universe is not a one-time event, but a single heartbeat in an eternal cosmic cycle. In this model, our expanding universe is simply the latest chapter. Before it, there existed a previous cosmos, one that was not born from a singularity, but was instead contracting under its own immense gravity, collapsing in on itself in a cataclysmic event called the Big Crunch. At the moment of greatest density, instead of vanishing into a point of infinite nothingness, something remarkable happens. The forces of nature, perhaps through quantum effects we do not yet understand, cause the universe to rebound. The contraction reverses and a new expansion begins. The Big Bang, in this view, is not a creation from nothing but a cosmic bounce. This violent transition from a crushing implosion to a furious explosion would have been a moment of unimaginable turbulence. Space-time itself would have been violently shaken, like a sheet of fabric being snapped. The resulting gravitational waves from that bounce would carry a unique signature, different from those predicted by inflation. They might show a specific pattern of polarization or contain echoes of the previous universe's structure imprinted within their frequencies. Finding that signature would be evidence that our universe had a parent, a grandparent, an endless lineage stretching back forever. It transforms the question from what started everything to what keeps the cycle going. Is our cosmos destined to expand forever, or will gravity one day pull it all back together, setting the stage for the next bounce and the next universe to be born from our ashes? Yet another source of those first space-time ripples might not be a single event, but a permanent feature woven into the cosmos itself. This is the theory of cosmic strings, and they are exactly what they sound like. In the searing heat of the universe's first moments, as it cooled and its fundamental forces separated from one unified state, physicists believe the fabric of reality may have developed flaws. Think of it like water freezing into ice. When water freezes, the molecules arrange themselves into a crystal pattern, but the process is not perfect. Defects form lines where the crystal structure doesn't align. In the early universe, these would not be ice crystals, but defects in the very fields that govern reality. These defects would manifest as unimaginably thin, yet incredibly dense strands of pure energy. A cosmic string is a one-dimensional crack in space-time, thinner than a proton but with the mass of a mountain range packed into every inch. They are not made of matter as we know it, but are kinks in the geometry of the universe itself, so dense that they warp space and time around them. If such a string passed through this room, you would not see it, but you would notice its effect as a gravitational lens, distorting the light from objects behind it. And these strings would not be static. They would form vast, tangled networks stretching across the cosmos, vibrating, whipping, and occasionally snapping. It is this violent motion that creates gravitational waves. When a cosmic string loop oscillates or when two strings cross and reconnect, they release tremendous bursts of energy in the form of space-time ripples. Unlike the single, initial burst from inflation or the bounce, a network of cosmic strings would produce a continuous background hum of gravitational radiation, a permanent whisper woven into the universe's foundation. Detecting that specific hum would be like finding the fossilized scars from the universe's birth pangs, evidence that the cosmos froze with imperfections, leaving behind ghostly threads that still vibrate with the memory of creation. The cosmic strings would hum with a constant vibration, but another theory suggests the early universe crackled with the violent collisions of countless tiny monsters. Among the most extreme ideas is that the first moments of creation spawned not just particles and radiation, but vast swarms of primordial black holes. These would not be the stellar mass black holes formed from collapsing stars, which take millions of years to appear. These would have been born directly from the intense pressure and density fluctuations in that seething infant cosmos. Picture the universe as a pot of water coming to a furious boil. As bubbles form and pop, imagine some of those bubbles collapsing under their own intense density, pinching off into tiny, separate pockets of reality so warped that nothing could escape. These would be black holes potentially as small as an asteroid or even a pebble in mass, yet containing all that mass within a microscopic point. A universe filled with such objects would be a chaotic, violent place. These black holes would zip around, drawn together by gravity, colliding and merging in spectacular events that would send powerful ripples through space-time. Each merger would be a tiny bang, a burst of gravitational waves adding to a cosmic cacophony. Furthermore, according to Stephen Hawking's work, very small black holes should slowly evaporate, radiating away their mass until they potentially vanish in a final, energetic pop. This evaporation process itself might also produce a distinctive signal. The combined effect of countless mergers, orbits, and evaporations over the eons would create a stochastic background of gravitational waves, a random, crackling static layered over the quieter hum from other sources. This static would be like listening to a rainstorm where you cannot distinguish individual drops but hear the collective roar. Even more intriguingly, if these swarms were dense enough, their collective gravity could have subtly sculpted the oldest light in the universe, the cosmic microwave background. Their shadows and influences might have left faint, patchy imprints on that primordial glow, a ghostly fingerprint of a universe once teeming with tiny, dark titans. Finding that signature would force us to rewrite cosmic history, revealing a dawn not of serene expansion, but of a dark, churning sea where the building blocks of reality were not just particles but countless voids. These ghostly threads and dark swarms paint a picture of a chaotic dawn, but what if our entire universe is merely a shadow cast by a collision in a higher dimension? This is the ekpyrotic universe, a theory born from string theory and the mind of physicists like Paul Steinhardt. It proposes that reality as we know it exists on a three-dimensional membrane or brain, floating within a hidden, higher-dimensional space. Picture our universe not as an expanding bubble, but as a vast, flat sheet, like a page in an unimaginably large cosmic book. Parallel to us, just a tiny distance away in this unseen dimension, floats another brain, another entire universe. For eons, these two brains drift silently, but gravity slowly draws them together. The collision is not a gentle touch, but a cataclysmic event. When they finally meet, the impact is titanic, flooding both brains with an immense concentration of energy and setting off the hot, dense expansion we call the Big Bang. In this model, our universe began not with an inflationary sprint, but with a big splat. This splat would have been a profoundly violent event, shaking the very fabric of our brain. The collision would send shockwaves rippling across our three-dimensional sheet of reality. These shockwaves are the primordial gravitational waves of the ekpyrotic scenario. But their character is fundamentally different from those of inflation, because the ekpyrotic model involves a slower, more gradual coming together of the brains. The resulting space-time ripples are predicted to be far weaker and to have a very different frequency signature. Inflation's violent, exponential stretch creates a broad, powerful spectrum of waves. The ekpyrotic splat, by contrast, would produce a much more subdued signal, one that might be nearly impossible to detect with our current instruments. This is a crucial distinction. If we one day detect the strong, telltale imprint of inflationary waves in the cosmic microwave background, it would strongly support the standard inflationary picture. If, however, we find nothing or find a pattern of waves that is much fainter and of a different character, the ekpyrotic model or another alternative becomes far more compelling. It suggests our cosmic genesis was not a spontaneous outburst from a singularity, but the reverberating echo of a collision between worlds we cannot see, in dimensions we cannot perceive, a cosmic accident that gave birth to everything we know. The collision of worlds in unseen dimensions is a staggering idea, but it still assumes our universe has the dimensions we perceive. The holographic principle challenges that assumption at its very core. It suggests that all the information describing our three-dimensional universe, every star, every planet, and every one of us, is actually encoded on a two-dimensional surface at its boundary, like a cosmic hologram. In this view, our rich, three-dimensional reality is a projection, an illusion generated from quantum data painted on a distant, flat screen. This is not science fiction, but a serious implication emerging from the physics of black holes and string theory. The principle arises from a profound puzzle about information. When matter falls into a black hole, what happens to all the information it contained? The holographic idea resolves this by suggesting the information is not lost inside, but is smeared and preserved on the black hole's event horizon, its two-dimensional surface. Extend this logic to the entire cosmos, and you arrive at a breathtaking possibility. Our universe, in its earliest moments, may have behaved like a black hole in reverse, with its entire future history imprinted on a primordial shell. This leads to a radical theory for the origin of cosmic structure. The galaxies and voids we see today might not have grown from three-dimensional quantum fluctuations stretched by inflation, but from two-dimensional quantum jitters on that primordial boundary. These jitters, these tiny bits of information flickering on the cosmic film, would have been translated into the three-dimensional density variations that seeded everything. And just as a shaky projector creates a blurry image, the process of projecting this two-dimensional data into our three-dimensional world would have created specific, detectable artifacts in the fabric of space-time. The gravitational waves from a holographic genesis would carry a unique statistical signature. their patterns across different frequencies would be subtly different from those predicted by standard inflation. They might show specific correlations or a distinct lack of power at certain scales, a kind of fingerprint left by the encoding process itself. Detecting that specific fingerprint in the primordial gravitational wave background would be perhaps the most dramatic evidence imaginable for the holographic principle. It would mean that the depth we experience, the very feeling of living in a three-dimensional world, is a magnificent and persistent illusion. Every gravitational wave we might one day detect from the dawn of time would not be a ripple in a three-dimensional fabric, but a vibration in the data on a two-dimensional surface, a cosmic message reminding us that reality is far stranger and far more interconnected than it appears. The holographic universe suggests our reality is a projection, but what if our entire cosmos is just one bubble in an endless frothing sea? This is the theory of eternal inflation, and it leads directly to the mind-bending concept of the multiverse. In this model, the inflationary sprint that gave birth to our universe never truly stopped everywhere. Instead, it continues eternally in a vast background reality called the false vacuum. Picture an infinite, bubbling pot of water that is always boiling. In this seething quantum foam, tiny pockets of stable reality can spontaneously form. A fluctuation in the energy field creates a bubble of true vacuum, a region where inflation ends. That bubble then expands at the speed of light within the eternally inflating background, becoming its own separate universe with its own laws of physics. Our entire observable cosmos is just one such bubble. We are living inside a cosmic froth that is constantly giving birth to an infinite number of other universes, each forever causally disconnected from our own. This process of bubble nucleation, the moment our universe pinched off from the false vacuum, would have been a violent quantum phase transition. It would be like a new soap bubble suddenly detaching from a larger soap film. The moment of detachment, the moment our universe became its own distinct entity, would have sent a shockwave rippling through the very structure of the bubble wall. This shockwave is a gravitational wave signature unique to our cosmic origin story within the multiverse. These waves would carry information not about the Big Bang itself, but about the precise moment our bubble universe was born from the eternal inflating sea. Their frequency and amplitude would be dictated by the energy difference between the false vacuum and our true vacuum, a fundamental number that defines our reality. Detecting this specific whisper would be the first direct, albeit incredibly faint, evidence that we are part of a multiverse. It would be an echo not of a beginning but of a separation. The gravitational waves would tell us that our universe is not alone, that our laws of physics are not special or fine-tuned, but simply the local bylaws of our particular cosmic bubble, one among an infinite, frothing ocean of other possibilities. It transforms the question from how our universe began to how our particular bubble of reality broke free from an eternal, generative chaos. The multiverse offers infinite possibilities, but our own universe might be filled with an invisible ocean, a field of energy that permeates every corner of space. This is the action field, and its hypothetical particle, the action, is one of the leading candidates to explain dark matter. Unlike the chaotic swarms of primordial black holes, actions are thought to be incredibly light, ghostly particles that barely interact with normal matter or light, which is why they are dark. They were not born in stellar furnaces, but are believed to have condensed out of the cooling universe in its very first moments, filling the cosmos like a fine, uniform mist. The action field is not static, however. In the dense, hot conditions after the Big Bang, this field would have been set into a coherent, universe-wide oscillation, like a vast bell ringing at a single, pure tone. As the universe expanded and cooled, this oscillation would have slowly lost energy. But that energy did not simply vanish. According to several compelling theories, the decaying oscillations of the action field could have transferred their energy directly into ripples in the fabric of space-time, generating a background of primordial gravitational waves. The process is akin to a weight suspended on a spring, bouncing up and down in a viscous fluid. Eventually, the bouncing slows, and the energy of the motion is dissipated into the fluid, creating waves. In the early cosmos, the action field was the bouncing weight, and the fabric of space-time itself was the fluid. Each oscillation that damped out sent a tiny pulse of gravitational energy rippling outward. Over the entire observable universe, countless such pulses would have combined to create a faint, persistent hum. This creates a profound and elegant link between two of cosmology's greatest mysteries. The same invisible substance that holds galaxies together, dark matter, could also be the very source of the universe's first whispers. If we can one day detect the specific frequency and pattern of gravitational waves produced by action decay, it would be a dual discovery, solving two puzzles with a single signal. It would tell us not only how space-time first rippled, but also what the unseen majority of our universe is actually made of. The dark that shapes the cosmos might have also given it its voice. The action field's gentle hum might have been one whisper, but the early universe could also have screamed. Another leading theory suggests the cosmos did not cool smoothly from its fiery birth. Instead, it underwent a violent, sudden shift in its fundamental state, a cosmic earthquake known as a first-order phase transition. Think of water boiling. At first, the water is liquid, a stable state. As you add heat, tiny steam bubbles begin to form and pop, but at the boiling point, the entire system becomes unstable. Bubbles of steam, representing the new, lower energy phase, nucleate randomly throughout the pot. These bubbles expand rapidly, collide, and merge until the entire pot of water has transformed into steam. The early universe, according to this theory, experienced something very similar. As it expanded and cooled, the fields that govern the forces of nature may have suddenly found a new, more stable configuration. This shift would not have happened everywhere at once. Instead, bubbles of this new, true vacuum would have spontaneously erupted within the old, high-energy, false vacuum that filled space. Each bubble would expand at nearly the speed of light, its wall a seething frontier of unimaginable energy. Now, envision this cosmic boiling pot on the scale of the entire infant cosmos. These expanding bubbles would quickly meet. When the walls of two bubbles collide, they do not simply merge quietly. The collision is a cataclysm. The immense energy contained in those walls is released in a spectacular burst, creating violent shockwaves that ripple through the primordial soup of particles and radiation. Critically, these shockwaves are not just in the matter. They are powerful distortions in the fabric of space-time itself. Each bubble collision is a hammer strike on the cosmic drum, generating a sharp burst of gravitational waves. As more and more bubbles collide and merge, the universe would have been filled with a cacophony of these space-time ripples, overlapping and combining into a loud, stochastic background roar. This signal would be very different from the smooth, broad-spectrum hum predicted by inflation. A first-order phase transition would produce a gravitational wave background with a much sharper peak at a specific frequency, a tone dictated by the energy of the transition and the speed of the bubble walls. It would be a more percussive, chaotic signature, the sound of the universe cracking into a new form. Detecting that specific tone would be like listening to a recording of the cosmos boiling, a direct echo of the moment when the very rules of reality snapped into the configuration we live with today. It would reveal a genesis not of serene expansion, but of explosive, bubble-by-bubble transformation, where every collision forged a piece of our cosmic destiny. The violent boiling of a cosmic phase transition paints a picture of a chaotic, energetic infancy. But what if the Big Bang itself was not the start of everything, but a moment of profound reversal? String theory offers a vision where our expanding cosmos was born from a previous era of collapse. This is the pre-Big Bang scenario. In this model, the universe we inhabit began not from a singularity of infinite density, but from a point of extremely high yet finite density. Before the Big Bang, there existed a long, slow epoch where the universe was contracting. It was shrinking, growing hotter and denser as all matter and energy were squeezed together. This was not a chaotic crunch, but a smooth, controlled deflation governed by the principles of string theory. During this contraction, the fabric of space-time would have been filled with the same kind of quantum jitters that exist today, tiny fluctuations at the smallest scales. As the universe shrank, these fluctuations were not erased. Instead, they were squeezed, amplified, and stretched by the contracting geometry. Think of a quiet room where someone begins to slowly turn up the volume on a speaker playing white noise. The sound waves, the fluctuations in air pressure, become louder and more pronounced as the room itself seems to close in. In the pre-Big Bang scenario, the quantum fluctuations in the gravitational field itself are that white noise, and the contracting universe is the hand turning up the volume. Then comes the pivotal moment, what physicists call the graceful exit. The contraction reaches a limit, a point where the density and temperature are immense but not infinite. Here, the unique properties of string theory take over. The fundamental strings that make up reality resist being compressed further, providing a cosmic bounce that reverses the collapse. The universe rebounds, transitioning from contraction to the expansion we see today. This graceful exit is the true Big Bang event. The crucial detail is what happens to those amplified quantum fluctuations during the bounce. They do not vanish or reset. They are imprinted onto the newborn, expanding universe as the seeds for all future structure. The most powerful of these amplified fluctuations would have been in the gravitational field itself. The violent transition from a long contraction to a sudden expansion would have shaken space-time like a rug being snapped, converting those amplified quantum whispers into a loud, clear signal of primordial gravitational waves. This predicted signal has a specific character because the fluctuations were stretched and amplified during a long, slow contraction phase. The gravitational wave background from a pre-Big Bang scenario would have a very distinct spectrum, tilted in a particular way across different frequencies. Finding that specific tilt in the cosmic hum would be a direct window into the pre-Bang era. It would be evidence that our universe has a past that stretches back before time as we measure it began, a ghostly memory of a cosmos that was once shrinking, holding within its contraction the blueprint for everything that was to come. The search for those first space-time ripples hinges on a single, crucial number known as the tensor-to-scalar ratio. This value, represented by the letter R, is the golden key cosmologists are trying to find. In simple terms, it measures the relative strength of primordial gravitational waves, the tensor modes, compared to the density fluctuations, the scalar modes that seeded galaxies. Think of it like listening to a recording of the Big Bang. The density fluctuations are the main melody, the variations that created all the structure we see. The gravitational waves are the background harmony, the deep bass notes that support the tune. The ratio R tells us how loud that harmony is compared to the melody. A high value for R means the gravitational wave signal is strong and prominent. A low value means it is faint, a subtle whisper beneath everything else. This single number carries immense weight because different theories of the universe's birth predict wildly different values for it. Simple, classic models of inflation, those with a single field rolling slowly down a gentle slope, typically predict a moderately high value for R. It is a clear, potentially detectable signal. If we find that strong signal, it would be a monumental confirmation of that straightforward inflationary picture. However, more complex and exotic theories predict a much quieter symphony. Models like the ekpyrotic universe with its colliding branes or certain string gas cosmology scenarios predict an R value so tiny it might be effectively zero with our current technology. A non-detection, a continued silence in the gravitational wave background would not be a failure. It would be a powerful message, loudly ruling out the simplest models of inflation and forcing us toward these more intricate alternatives. The quest to measure R is therefore a process of elimination on a cosmic scale. Every experiment that pushes the sensitivity lower is not just listening harder, it is narrowing down the list of possible origin stories for our entire reality. The value of this ratio will tell us if the universe's birth was a loud, violent event or a much more subtle and complex transition. It is the number that will decide which of these 30 theories moves from fascinating speculation into the realm of confirmed cosmic history. While the inflattened field was the engine of cosmic inflation, it may not have been working alone. A more subtle player could have been present, a spectator field that watched the drama unfold without driving the expansion itself. This spectator field would have been a passive component of the early universe, a separate quantum field that existed alongside the inflaton but with a much smaller energy, simply riding along during the inflationary sprint. Its name is literal, it spectated, but in the seething quantum foam of that epoch, being a spectator did not mean being silent. This field would have had its own tiny quantum fluctuations, minute ripples in its value across space. Normally, these ripples would be insignificant and quickly fade. However, the incredible stretching of space during inflation can dramatically alter their fate. If the spectator field interacts with the inflattened field in a specific way, perhaps through a shared coupling or a resonance, something remarkable can happen. The rapid expansion can act like a cosmic amplifier for the spectator's fluctuations, boosting them from quantum whispers into classical, large-scale waves. This amplification process is not gentle. It is a violent transfer of energy from the inflationary expansion into the spectator field's oscillations. And when any field oscillates with that much energy on a cosmic scale, it shakes the fabric of space-time. The spectator field, once passive, becomes an active source of primordial gravitational waves. The signature of this mechanism is particularly intriguing. While standard inflation typically predicts a red-tilted spectrum for gravitational waves, meaning their power decreases at higher frequencies, a spectator field can produce the opposite, a blue-tilted spectrum. This means the gravitational wave signal would actually rise and become stronger at higher frequencies. Imagine listening to a chord from the Big Bang. The standard inflationary chord would have the deepest bass notes as the loudest. A spectator field chord would have the higher-pitched notes ringing out more clearly. This blue tilt is a potential smoking gun. If future detectors like space-based laser interferometers find a rising hum of gravitational waves at specific high frequencies, it could point directly to the presence of this silent partner in the early cosmos. It would reveal that inflation was a more complex symphony than we thought, with a duet between the lead inflaton and a resonant spectator, together composing the first ripples in reality. The spectator field's high-pitched hum would be a specific clue, but the true frequency of the universe's first whispers might reveal an even grander unification. The energy at which inflation occurred is not a random number. It is staggeringly high, around 10 to the 16 billion electron volts. This figure is not just immense, it is eerily familiar to particle physicists. It is the grand unification scale. This is the energy, the temperature, at which three of the four fundamental forces of nature, the electromagnetic force, the weak nuclear force, and the strong nuclear force are theorized to merge into a single, unified superforce. This moment of perfect symmetry existed only in the first split second after the Big Bang, a fleeting instant forever beyond the reach of any particle collider we could ever build on Earth. Our most powerful machines, like the Large Hadron Collider, probe energies trillions of times lower. We cannot recreate the GUT scale, we can only look for its echoes. This is where primordial gravitational waves become our time machine. The strength of the gravitational wave signal, that crucial tensor-to-scalar ratio, is directly tied to the energy scale of inflation. A loud, clear detection would tell us the exact energy at which the universe underwent its exponential sprint. If that measured energy aligns perfectly with the predicted duty scale, it would be a revelation. It would mean we are indirectly probing the physics of that first unified moment. Detecting those waves would be like finding a fossilized recording of the duty symphony itself. The ripples in space-time would carry the imprint of the universe's state when all forces except gravity were one. They would be a vibrational artifact from the epoch when the cosmos was simple, symmetric, and governed by a single law. This connection transforms the search from a cosmological endeavor into a fundamental physics experiment. We are not just listening for how the universe expanded, we are listening for the moment it fractured. The separation of the forces as the universe cooled, a process called symmetry breaking, would have been a cataclysmic event shaking the fabric of reality. Those tremors could be preserved in the gravitational wave background. So, a successful detection does more than confirm inflation. It provides the first and only experimental evidence for grand unification, offering a glimpse into the laws of physics at energies we can never directly touch. It would tell us that our mathematical dreams of a unified theory are not just elegant speculation, but a description of the universe's first and most powerful state. The faintest whispers in the cosmos could thus answer one of the deepest questions in all of science. Are all forces truly one? The search for a grand unified force points to a single, dominant engine for creation. Yet some models suggest the cosmic symphony required multiple soloists. Enter the curvaton, a secondary field that may have played a starring role in shaping our universe. In this alternative to standard inflation, the primary inflaton field still drives the rapid expansion, but it does a surprisingly quiet job. Its own quantum fluctuations, the seeds for future structure, are remarkably weak. The universe inflates smoothly but leaves behind a canvas that is almost blank. This is where the curvaton takes the stage. This secondary field is essentially dormant during inflation, a spectator like others we have discussed. But it possesses a crucial property. Its energy density does not dilute away as quickly as matter or radiation after inflation ends. As the hot Big Bang era begins, the inflaton's energy decays into the primordial soup of particles. The curvaton's energy, however, persists, becoming a more and more significant fraction of the total energy budget of the cosmos. It is a slow-burning fuse. Eventually, when the universe has cooled sufficiently, the curvaton field itself decays. This decay is not a silent exit. It converts all of its stored energy into the very particles and radiation that fill the universe, but it does something more profound. The tiny quantum fluctuations that were imprinted on the curvaton field during inflation are now amplified and imprinted onto this newly released energy. In this model, the curvaton's fluctuations, not the inflatons, become the primary source of all the density variations that later collapse into galaxies and clusters. The main melody of the cosmos was composed not by the lead singer, but by the backup vocalist who stepped into the spotlight at the last moment. But what does this have to do with space-time ripples? The curvaton's decay is a violent, inhomogeneous process happening across the entire universe. As it releases its energy, it does not do so perfectly evenly. The process creates pressure waves in the hot plasma, massive compressions and rarefactions rippling through the infant cosmos. These are not gentle waves. They are tsunamis of energy crashing through the primordial medium. Such violent, large-scale motions do not just stir up matter, they vigorously shake the fabric of space-time itself. The result is a significant background of gravitational waves generated not during inflation, but afterwards during the decay of the curvaton field. This offers a fascinating alternative origin story for the primordial hum. We may be listening not to the tremors of the inflationary sprint itself, but to the aftershocks of the curvaton's grand finale. The gravitational wave signature from this mechanism would carry its own distinct markers. it could produce a different relationship between the strength of the density fluctuations and the gravitational waves, potentially allowing for a detectable signal even if inflation occurred at a much lower energy scale than the grand unification point. It decouples the two key signatures of the early universe, suggesting the seeds of structure and the first ripples in space-time might have two different, though connected, parents. Finding evidence for the curvaton would reveal a more layered and intricate genesis, where the universe's form and its gravitational echo were crafted in separate, decisive acts. A ghost condensate is not a phantom in the machine, but a state of matter so strange it seems to invert the laws of physics. It arises from a theoretical scalar field that, under certain conditions, develops what physicists call a negative kinetic energy. Kinetic energy is the energy of motion, the very thing that makes a rolling ball keep rolling. We are taught it must always be positive. A negative kinetic energy defies that intuition, suggesting a form of motion that, in a sense, feeds on itself in unexpected ways. In the early universe, such a field could have settled into this ghostly phase, forming a uniform, exotic condensate that permeated all of space. This condensate would not be static. Like a vast, invisible ocean, it would support waves and oscillations, ripples in its own value. But because of its inverted energy properties, these waves behave bizarrely. Their propagation can be different from anything we know, potentially allowing them to travel at speeds other than light, or to interact with gravity in counterintuitive ways. The true cosmic drama occurs when this ghost condensate decays or undergoes a phase transition back to a normal state. That shift would be a moment of profound instability for the fabric of reality. The exotic energy of the condensate must go somewhere, and as it dissipates, it can flood the universe with a burst of radiation and, critically, a powerful surge of gravitational waves. The signature of these waves would be unmistakably odd. They could possess a spectrum that is blue-tilted like the spectator field, but potentially even more extreme, with immense power concentrated at very high frequencies. They might also exhibit a distinct form of polarization, a specific twisting in the way they stretch and squeeze space that standard inflationary models simply do not produce. Detecting such an anomalous signal would be a direct challenge to our standard assumptions. It would force us to accept that the infant universe experimented with phases of existence where the most fundamental concepts of energy and motion were turned inside out. The ghost condensate suggests that before settling into the stable, predictable laws we observe today, reality may have passed through a fleeting, phantom stage, a spectral epoch whose only remaining trace is a faint, peculiar tremor in the cosmic background, a whisper from a time when physics itself was haunted. The ghost condensate hints at a universe where energy behaved unnaturally, but another theory suggests the infant cosmos was not a cold, empty void during its most dramatic growth spurt. Standard inflation is often described as a supercooled expansion, where the inflattened field rolls down its potential energy hill in near isolation. Its energy preserved until it decays in a sudden, explosive reheating that fills the universe with heat. This is cold inflation. Warm inflation proposes a radically different environment. In this model, the inflattened field does not roll in splendid isolation. Instead, it is rolling through a dense, hot plasma from the very beginning. As it moves, it constantly dissipates its energy, like a ball bearing sinking through a jar of honey, generating heat continuously throughout the inflationary period. There is no separate reheating phase at the end because the universe was already warm. This constant friction between the inflaton and the thermal bath has profound consequences. In cold inflation, the quantum fluctuations that seed galaxies are born in the quiet of the empty, accelerating space. In warm inflation, those fluctuations are not purely quantum. They are primarily thermal. The inflattened field is constantly jostled by the intense heat of the surrounding plasma. These thermal kicks generate the density fluctuations that will later structure the cosmos. Think of it like the difference between a single musician playing a note in a soundproof room versus that same musician playing in a bustling, noisy factory. The note in the room is pure and quantum. The note in the factory is shaped and amplified by the surrounding clamor. This shift from quantum to thermal origin changes everything about the predicted signals. For primordial gravitational waves, the implications are dramatic. Gravitational waves are ripples in the geometry of space-time itself. The thermal bath of particles, no matter how hot, does not directly produce these geometric ripples with the same efficiency as the raw, quantum gravitational fluctuations of cold inflation. In warm inflation, the thermal noise dominates the density fluctuations, but the gravitational waves remain primarily quantum in origin. This creates a mismatch. The scalar density fluctuations become relatively stronger, while the tensor gravitational waves remain relatively weaker. The result is a significant suppression of the tensor to scalar ratio. The predicted gravitational wave signal from warm inflation is much fainter than in its cold counterpart. If the universe underwent warm inflation, the primordial space-time ripples we are searching for could be so quiet they might forever elude our detection. A confirmed non-detection by increasingly sensitive experiments would therefore not just rule out simple cold inflation. It would become positive evidence for this warmer, noisier, and more interconnected birth. It paints a picture of a cosmos that never knew a cold, lonely infancy, but was born in a state of constant frictional heat, its structure forged not in quantum silence, but in the relentless roar of a primeval fire. The warmth of the plasma in warm inflation smooths out the statistical story, but other models predict a cosmos born with a distinct fingerprint of complexity. Most standard theories assume the primordial fluctuations, those seeds for galaxies, were Gaussian. This is a statistical term meaning they were simple, random, and bell curve symmetric, like the static on an old television screen. Each point in the early sky was an independent roll of the cosmic dice. But what if the dice were loaded? Non-Gaussianity refers to deviations from this perfect randomness, revealing subtle correlations and patterns in the primordial noise. Imagine that static on the screen occasionally forming into faint, recurring shapes like brief swirls or clusters of specks. That would be non-Gaussian. These patterns are a powerful clue because different physical processes in the early universe leave different statistical imprints. Crucially, many of the same inflationary models that produce a detectable signal of primordial gravitational waves also predict specific, measurable types of non-Gaussianity. This creates a powerful two-pronged test. For instance, models with multiple interacting fields, like certain versions of the Curvaton scenario, or models where the inflattened field takes a sharp turn on its energy landscape, can simultaneously generate both a background of gravitational waves and a distinct non-Gaussian signature in the way the cosmic microwave background is speckled. The gravitational waves tell us about the energy scale of the event. The non-Gaussianity tells us about the interactions and the number of players involved. By combining data from gravitational wave observatories, which listen for the tensor hum, with exquisitely detailed maps of the cosmic microwave background from telescopes, which look for these statistical swirls, cosmologists can perform a kind of cosmic triangulation. If we detect gravitational waves with a certain strength, and in the same breath find a specific pattern of non-Gaussianity in the CMB, it would be a match to a single, precise model. It would rule out thousands of other possibilities. This combination moves us from simply knowing that inflation happened to understanding exactly how it happened. The shape of the energy landscape, the dance of the fields, the precise mechanics of Genesis. The search is not for one whisper, but for a chorus where the notes and the rhythm together compose the true song of the beginning. The universe's first whispers might not have been a simple hum, but a twisted spiral. Standard physics treats the fabric of space-time as impartial, affecting matter and energy without a preferred direction. but a radical modification to Einstein's theory, known as Chern-Simons gravity, introduces a cosmic bias. In this framework, a special mathematical term is woven into the equations of gravity itself. This term does something extraordinary. It makes gravity sensitive to a concept called handedness or chirality. You can see this in your own hands. Your left and right hands are mirror images, but you cannot rotate one to perfectly match the other. They have opposite chirality. In Chern-Simons gravity, the equations treat left-handed and right-handed gravitational waves differently. As these primordial ripples travel through the modified fabric of space-time, one polarization, say left-handed, might travel slightly faster or slower than the right-handed one. It is as if the cosmos itself has a subtle twist, a preferred direction of rotation imprinted into its fundamental laws. This would not just be a minor detail. Over the vast distances from the edge of the observable universe to our telescopes, that tiny difference would accumulate. The primordial gravitational wave background would not arrive as a simple, random jumble of stretches and squeezes. Instead, it would carry a net circular polarization, a distinct swirling pattern in the way space-time was disturbed. Imagine the difference between a flat, vibrating drumhead and one that is subtly, consistently spiraling as it vibrates. Detecting that spiral fingerprint would be a revolution. It would be direct evidence that gravity is not exactly as Einstein described it on the largest scales, and that the universe at its birth possessed a fundamental handedness, a cosmic preference for left over right or right over left. This twist could be a relic from the moment the forces of nature split apart, a frozen memory of a time when the laws of physics were not symmetrical. Finding it would mean the first ripples in reality were not just echoes of an event, but encoded messages about the very nature of the stage upon which the drama unfolded. A cosmic twist in gravity would rewrite our laws, but a whisper from the very first particles could do the same. Supersymmetry is a grand, unproven theory of particle physics that proposes every known particle has a hidden superpartner. The electron would have a selectron, the quark a squark, the photon a photino. This elegant symmetry is theorized to have been perfect in the universe's first, unimaginably hot moments. All particles and their superpartners would have been indistinguishable, part of a single, unified family. But as the cosmos expanded and cooled, this perfect symmetry had to break. The superpartners gained mass, splitting off from their familiar counterparts and becoming the heavy, hidden shadows of the particle world we know. This spontaneous breaking of supersymmetry was not a quiet event. It was a phased transition in the fundamental fields of reality, and according to some compelling models, it likely occurred during the inflationary epoch itself. As the inflattened field drove the exponential expansion, it also triggered the fall of supersymmetry. The energy released in that breaking would have been colossal, flooding the infant universe with a burst of exotic, supersymmetric particles. These newly minted superpartners, like the Gravitino or the Inflatino, would have been unstable. They could not last in the cooling cosmos. Their decay, cascading down into lighter particles, would have been a series of violent, energetic events happening everywhere at once. Each decay would have been a miniature explosion, releasing energy not just as radiation, but as ripples in the fabric of space-time. The collective din of countless superpartner decays would generate a specific background of primordial gravitational waves. This signal is a direct bridge between the microscopic and the cosmic. The frequency and amplitude of these waves would be dictated by the mass scale of the superpartners, a number particle physicists have been desperately trying to pin down for decades. If we could detect this specific hum, it would tell us the energy at which supersymmetry broke. We would finally know the masses of these elusive shadow particles without ever smashing a single proton in a collider. The cosmos itself would have recorded the data in its oldest vibrations. It transforms the search for primordial gravitational waves into a hunt for the fingerprints of the entire supersymmetric family. offering a single, elegant solution to two of physics' greatest puzzles: what shaped the universe's infancy and what completes the particle zoo at its most fundamental level. The first whispers might carry the names of particles we have never seen, echoing from a time when every bit of reality had a perfect, hidden twin. The decay of the inflattened field was not a gentle sigh. After inflation's breathtaking sprint, the universe was left cold and empty, a vast expanse of stretched space containing only the dormant energy of the inflattened field itself. To birth the hot, particle-filled cosmos we know, that energy had to be unleashed in a cataclysm known as reheating. This was the moment the universe truly caught fire. The inflattened field, having rolled to the bottom of its energy hill, began to oscillate. Think of it as a giant cosmic pendulum swinging back and forth with unimaginable energy. But this was no ordinary pendulum. As it oscillated, it did not simply lose energy to friction. Instead, through a process called parametric resonance, it transferred its energy with explosive efficiency into other quantum fields, the fields that would become all the quarks, electrons, and photons of creation. Parametric resonance is like pushing a child on a swing. If you push at just the right moment in the swing's arc, even a small push can create a huge, amplified motion. In reheating, the oscillating inflattened field acts as that perfectly timed push, but for an entire universe's worth of quantum swings. Specific frequencies in the particle fields resonate, growing exponentially from microscopic whispers into towering waves of real particles. The process is violently non-linear and chaotic. It is less like lighting a fire and more like detonating a bomb made of pure potential energy. Space itself becomes a seething, turbulent plasma, filled with clumps and bursts of energy colliding and merging. This is where the gravitational waves emerge. Such extreme, rapid, and inhomogeneous energy transfer does not happen smoothly. The violent churning of the newly created particle soup, the collisions of energy bubbles, and the very oscillations of the inflattened field itself shake the fabric of space-time with incredible force. The reheating era would have been a crescendo of sound following the silent expansion of inflation. The gravitational waves produced during this brief, frenzied period would form a distinct background, one with a characteristic peak at very high frequencies. Their signature would tell us not about the start of inflation, but about its spectacular end, the moment the universe transformed from a cold, empty void into a raging primordial furnace. Detecting this specific high-frequency hum would be like hearing the crackle of the first fire, the precise instant our universe filled with the heat and light that would eventually lead to stars, planets, and us. Reheating filled the cosmos with a chaotic fire, but the early universe might have also been carved into distinct, frozen territories. This leads us to domain walls, two-dimensional sheets of pure energy that could have formed as a cosmic afterthought. When the universe cooled and its fundamental fields settled into their current state, they may not have chosen the same value everywhere. Picture a vast sheet of paper being crumpled. As you flatten it, some sections face up while others face down. In the cosmos, the field representing the universe's state could have randomly settled into different but equally stable configurations in separate, enormous regions. The boundaries between these regions are the domain walls. They are not physical barriers, but defects in the fabric of reality itself, incredibly thin surfaces where the field value changes abruptly. A single domain wall would be a flat, two-dimensional sheet stretching across a significant fraction of the observable universe, possessing a staggering surface density. If such a wall passed through our solar system, its gravitational influence would be devastating, warping planetary orbits beyond recognition. Thankfully, cosmologists believe that if domain walls formed, they likely did not exist in isolation. Instead, they would have created a tangled, labyrinthine network, like a vast, chaotic honeycomb dividing space into countless cells, each with a slightly different internal law of physics. This network would be dynamic and unstable. the walls feel a tension pulling them taut, and they will move to minimize their total area. Over cosmic time, the network would simplify, with walls colliding, reconnecting, and annihilating each other. The final annihilation of these vast, energetic sheets would be a spectacle of cosmic destruction. When two walls meet, they do not just merge quietly. They can completely annihilate, converting all their immense surface energy into a furious burst of radiation and particles. This is not a single event, but a final, universe-wide fireworks display as the last remnants of the network violently vanish. Each annihilation is a hammer blow on the cosmic drum. The rapid, large-scale conversion of such concentrated energy into other forms would violently shake the fabric of space-time, generating powerful bursts of gravitational waves. Because the walls are all of a similar scale and mass, and because they would annihilate in a relatively short cosmic period, the gravitational waves they produce would not create a broad hum. Instead, they would coalesce into a sharp, distinct peak at a specific frequency. It would be a clear, resonant tone in the gravitational wave background, like a single, powerful chime ringing out across the eons. Detecting that precise peak would be a direct echo of the universe's fragmentation and subsequent healing, a signal that our cosmos was once a patchwork of different realities, whose borders ultimately collapsed in a final, resonant crash, leaving behind only a pure note in the silence. That final, resonant crash from annihilating domain walls would have been a powerful event, but the universe's history may have included an era where space itself behaved like a rigid, unyielding medium. This is the theory of a Canation-dominated era. After inflation ended and the universe reheated, we typically picture a cosmos filled with a hot, relativistic plasma of particles zipping around at near light speed. But an alternative scenario suggests a different, more extreme phase took hold first. Imagine the inflattened field, having driven the expansion, did not simply decay away into particles. Instead, it kept rolling rapidly down its potential energy hill, converting its stored potential energy almost entirely into pure kinetic energy, the energy of motion. For a brief but crucial period, this fast-rolling scalar field became the dominant component of the entire cosmos. Its energy density was not in heat or mass, but in the sheer, relentless motion of the field itself. This creates what physicists call an ultra-stiff equation of state. In this state, the pressure is incredibly high, almost equal to the energy density. A universe dominated by such a field expands in a very specific, aggressive way. It cools and dilutes much faster than a universe filled with radiation or matter. Space stretches in a manner that prioritizes this pure kinetic energy above all else. Now, consider any gravitational waves that might have been generated just before or at the start of this Canation era. These could be waves from the final moments of inflation, from preheating resonances, or from the decay of cosmic defects. In our standard cosmic history, these high-frequency waves would have simply redshifted away, their wavelengths stretched to undetectable lengths by the subsequent expansion dominated by radiation and matter. But in a Canation era, something extraordinary happens. The ultra-stiff expansion actually amplifies these gravitational waves as they travel. It is as if the fabric of space-time itself, behaving like a taut drumhead, resonates with and boosts the high-frequency ripples passing through it. The Canation field's kinetic energy pumps energy into the waves, preventing them from fading as they normally would. This amplification is not uniform. It preferentially boosts gravitational waves at very high frequencies. The result would be a gravitational wave background with a dramatic blue-tilted spectrum, a sharp peak screaming at frequencies far higher than those from inflation alone. Detecting such a signal would be like finding a fossilized recording of the universe's teenage years, a period of wild, kinetic dominance that left its mark by supercharging the echoes of earlier cosmic violence. It suggests our cosmos passed through a phase where motion itself was king, a fleeting epoch where the role of a field shaped space so severely that it turned whispers from creation into shouts we might still hear today. String theory paints a universe of hidden geometry, where every point in our familiar three-dimensional space conceals a tiny, curled-up labyrinth of extra dimensions. These are not large, empty directions we can travel, but microscopic shapes perhaps as small as the Planck length. The properties of these hidden shapes are not fixed. They are described by moduli fields, cosmic dials that set their size, shape, and topology. In the universe's first fiery moments, these dials were not set. Every possible configuration of the extra dimensions was in a frantic quantum superposition. The cosmos was a symphony of potential geometries, all playing at once. Then, as the universe expanded and cooled, a profound transition had to occur. The moduli fields had to find their resting values. This process, called moduli stabilization, is how the extra dimensions snapped into their specific, stable form, locking in the fundamental constants of our reality. But this snapping was not a gentle click. Finding their stable points involved violent relaxation. Picture a vast, complex landscape of hills and valleys, where each valley represents a possible stable configuration for the extra dimensions. The moduli fields began high on the slopes, rolling and tumbling down toward their respective valleys. As they fell, they gained tremendous kinetic energy. Upon reaching the valley floor, they did not stop. They oscillated wildly, like a ball bouncing back and forth in a deep bowl with immense amplitude. These were not small quivers. They were universe-spanning oscillations in fields that are directly coupled to gravity itself. Each massive oscillation represented a huge, shifting concentration of energy, and with each pass through the minimum, the field would decay, shedding its energy by producing particles and, crucially, ripples in space-time. Because there are many different moduli fields, each describing a different aspect of the hidden geometry, the early cosmos would have been filled with a chorus of these decaying oscillations. Each one would produce gravitational waves at a frequency set by its mass, which is tied to the scale of the extra dimensions. The result would be a gravitational wave background with a rich, multi-peaked spectrum. It would not be a single hum or a smooth curve. It would be more like a cosmic chord with several distinct notes ringing out simultaneously. Each note corresponds to the stabilization of a different piece of the universe's hidden anatomy. Detecting such a complex signal would be the ultimate confirmation of string theory's geometric vision. It would be a direct audio recording of the extra dimensions crystallizing into their final form. Those gravitational waves would tell us not just that extra dimensions exist, but their size, their shape, and the very process by which they became the immutable foundation of our physical laws. The first ripples in space-time could carry the blueprint of reality's complete architecture, a vibrational map of every hidden fold in the cosmos. The universe's hidden geometry may have stabilized into a fixed chord, but some models suggest the cosmos itself is a perpetual pendulum. A specific cyclic model proposes that our expanding universe is just one phase in an endless loop, and the transition between cycles is not a simple crunch. It passes through a bizarre anti-gravity phase. In this theory, a ghost-like field, similar to the ghost condensate but acting on a cosmic scale, temporarily dominates the universe. As the previous cycle ends and contraction begins, this field activates. Its unusual properties cause gravity, the force that pulls everything together, to effectively reverse its sign. For a fleeting moment, the universe experiences anti-gravity. Instead of pulling matter and space inward, gravity pushes outward, acting as a cosmic repulsive force that halts the collapse. This anti-gravity bounce is the pivotal moment that turns a big crunch into a new Big Bang, a cosmic rebound powered by repulsion rather than collision. The passage through this exotic phase is incredibly violent and rapid. Space-time is stretched and squeezed in opposing directions in quick succession, subjected to forces that defy our everyday experience of reality. Such a profound disturbance does not leave the universe untouched. It violently shakes the very fabric of space-time, generating a powerful burst of primordial gravitational waves. However, the signature of these waves is what makes this theory truly testable. The unique, oscillatory nature of the bounce, the rapid flip from contraction to antigravity-driven repulsion to expansion, imprints itself on the gravitational waves in a very specific way. It affects their polarization, the pattern of how they stretch and squeeze space. As these waves travel through the universe, they interact with the oldest light we can see, the cosmic microwave background. The oscillatory, twisting motion from the antigravity bounce would leave a distinct, swirling pattern in the polarization of that ancient light, a kind of curly fingerprint known as a B-mode signal with a specific oscillatory signature. Finding that exact pattern in the CMB would be like discovering a cosmic seismograph reading from the bounce itself. It would tell us that our universe did not begin from a singularity, but rebounded through a ghostly epoch where the most familiar force in the cosmos turned inside out, pushing the universe into a new existence with a powerful, repulsive shove. Gravitons are the hypothetical particles that carry the force of gravity, just as photons carry light. If the early universe was a seething, hot plasma, it should have been filled with these gravitational messengers. Every collision, every burst of energy in that primordial fire would have shaken the fabric of space-time, generating gravitons. And just as the cosmic microwave background is the cooled, redshifted remnant of the ancient photon bath, there must logically be a cosmic gravitational wave background of these particles, a thermal graviton background. Its temperature is directly tied to the temperature of the universe at the moment these gravitons effectively stopped interacting and traveled freely. Calculations place that temperature at just under 1 billion degrees Kelvin, a searing heat that corresponds to gravitons with frequencies around 100 gigahertz. That is a whisper in the radio band, but a whisper of a fundamentally different nature. The reason this thermal background is so incredibly faint, utterly drowned out by every other source we have discussed, comes down to gravity's weakness. Gravity is the feeblest of all the fundamental forces by an almost incomprehensible margin. A single magnet can lift a paperclip, defeating the gravitational pull of the entire Earth. In that hot early soup, while photons, quarks, and electrons were constantly slamming into each other, gravitons were barely produced. Their interaction probability is so minuscule that the universe was essentially transparent to them from the very first instant. They were never in thermal equilibrium with the rest of the cosmic plasma. So while the thermal graviton background is a real, predicted component of our cosmos, its signal is a ghost of a ghost. Its intensity is estimated to be dozens of orders of magnitude fainter than even the most optimistic inflationary gravitational wave signals. This presents a profound and humbling experimental wall. Detecting this specific thermal whisper is, with any technology we can currently conceive, impossible. It is the quietest possible echo from the hot Big Bang, a fundamental murmur that confirms our understanding of gravity's place in the cosmos precisely by being forever out of reach. Its overwhelming faintness is not a flaw in the theory, but a stark signature of gravity's lonely, detached role in the symphony of creation. Beyond the faintest thermal whisper lies a realm where space-time itself loses its smooth classical nature. The fabric of reality, when examined at the smallest possible scales, is theorized to dissolve into a chaotic, frothing sea known as quantum foam. This is not a metaphor, but a direct prediction from marrying quantum mechanics with general relativity. At the Planck scale, distances so tiny that a trillion of them could fit across a proton, the orderly geometry of Einstein's universe breaks down completely. Here, the concepts of here and there, before and after, cease to have clear meaning. Space-time becomes a probabilistic storm. Microscopic wormholes may blink in and out of existence. Tiny regions of space may pinch off into separate bubbles or undergo violent, random fluctuations in curvature. It is a seething, turbulent foam at the foundation of everything. In the universe's very first instance, the entire cosmos existed at this unimaginable scale. For a fleeting moment, all of reality was quantum foam. As the universe expanded and cooled, this foam would have frozen or coalesced into the smooth, four-dimensional continuum we experience today. But that transition from quantum chaos to classical order would not have been silent. The violent churning and popping of the foam's structure, the rapid formation and annihilation of these microscopic spacetime bubbles would have generated ripples. Each quantum fluctuation in geometry would have been a tiny tremor in the gravitational field itself. Collectively, these countless random tremors would have produced a stochastic background of gravitational waves with a very distinct character. Because the foam operates at the Planck scale, the waves it generates would be of extremely high frequency and incredibly short wavelength. The signal would be a cosmic hiss, a sizzle of white noise at frequencies far beyond what any current or planned detector could ever hope to hear. This hiss is more than just another source of primordial waves. It represents the ultimate signal, a direct recording of quantum gravity in action. Detecting it, even in principle, would be like listening to the individual pops and fizz of the universe's foundational substrate. It would confirm that at its heart, space-time is not a static stage but a dynamic, probabilistic entity. The quantum foam's hiss is the sound of reality itself being woven from uncertainty, a permanent, if utterly faint, reminder that the smooth cosmos we perceive is an emergent illusion, built upon a foundation of endless, frothing change. Two of the universe's deepest mysteries might share a single origin story: the invisible substance that sculpts galaxies and the first ripples in space-time could be different echoes of the same ancient event. Several compelling theories propose that the very processes which generated primordial gravitational waves also manufactured dark matter, weaving the cosmic fabric and its hidden scaffolding from the same primordial thread. One elegant scenario involves the decay of the inflaton field itself. After driving the exponential expansion of inflation, the inflaton must eventually decay, transferring its immense energy into the hot soup of the standard model particles. But what if it did not decay into all known particles equally? A slight asymmetry, a preference in the way it couples to other fields, could mean a significant portion of its energy cascaded into a completely new, stable particle that barely interacts with light or ordinary matter. This particle would be a perfect candidate for dark matter. Its production would have been sudden and universal, a flash creation event across the entire cosmos. And crucially, the decay of the inflaton is not a silent process. The violent, inhomogeneous transfer of energy shakes space-time, producing a distinct background of gravitational waves from preheating. In this model, the strength and frequency of those gravitational waves are directly tied to the mass and abundance of the dark matter particles created. The louder the gravitational wave signal from reheating, the more dark matter was forged in that instant. Another profound link comes from the action, the ghostly particle we met earlier. As the action field oscillated in the early universe, its coherent motion not only could have generated gravitational waves, but also, as it lost energy, it would have condensed into a cold, ultra-light particle that now fills the cosmos as dark matter. Here, the dark matter is not a byproduct of decay, but the field itself settling into its lowest energy state. The gravitational waves are the sound of that settling process. Even cosmic strings, those one-dimensional cracks in space-time, offer a dark matter connection. As a network of strings evolves, it can release not only gravitational waves but also loops that pinch off and collapse. These collapsing loops could be prolific producers of super-heavy, stable particles. If those particles survived to the present day, they would form an extremely massive, rare form of dark matter, with its abundance dictated by the dynamics of the string network. The gravitational wave background from the strings would then be a direct tracer for this exotic dark matter's birth. Finding a specific gravitational wave signal and matching it to the observed properties of dark matter would be the ultimate cosmic unification. It would tell us that the unseen majority of our universe's mass and the first tremors in its fabric are not separate puzzles, but two verses of the same creation hymn. The magnetic monopole problem was a crisis that almost broke cosmology. A monopole is a hypothetical particle with a single magnetic pole, a north without a south, a fundamental magnet that cannot be cut in half. Grand unified theories predicted these exotic objects should have been produced in staggering numbers during the universe's first split second as the unified force fractured. The math was clear. There should be at least one monopole in every volume of space the size of your fist, making them more common than atoms. Their immense mass and magnetic charge would have dramatically altered the evolution of the cosmos, clumping matter, draining energy, and leaving observable scars we simply do not see. The universe, for some reason, is devoid of these magnetic monsters. This glaring contradiction was one of the key motivations for Alan Gut's theory of cosmic inflation. The idea was brilliant. The exponential expansion of space would have stretched the universe so rapidly that it diluted the monopole density to virtually zero, sweeping them away into the unobservable vastness beyond our cosmic horizon. Inflation solved the problem by making monopoles incredibly rare. But what if they were not entirely erased? What if a tiny population survived and their very rarity led to another, more subtle cosmic signature? This brings us to a startling possibility known as the monopole catalysis of proton decay. A magnetic monopole is not just a magnet. In the presence of certain grand unified theories, it can act as a catalyst, a trigger for matter to unravel. If a proton, the stable heart of every atom, were to encounter a magnetic monopole, the interaction could cause the proton to disintegrate instantly. The proton would decay into lighter particles like pions and positrons, releasing a burst of energy in the process. Normally, protons are incredibly stable, with lifetimes longer than the age of the universe. But in the presence of a monopole, that stability vanishes. Now, imagine the early universe after inflation. It is still incredibly dense and hot. The few surviving monopoles are zipping through the seething plasma, and everywhere they go, they leave a trail of destruction. Each collision with a proton or atomic nucleus is a tiny, violent event. A proton that has existed for a microsecond suddenly vanishes in a flash of energy. This is not a chemical reaction. It is a fundamental transformation of matter, mediated by a relic from the grand unification epoch. The collective effect of countless such catalyzed decays across the infant cosmos would have been a pervasive source of energy release. But more than that, each decay event is a sudden, localized explosion. The rapid conversion of mass into other forms in such an inhomogeneous way, following the random paths of the monopoles, would have created pressure waves and shocks in the primordial plasma. These are not gentle ripples, they are sharp, percussive disturbances, and just as a drum head vibrates when struck, the fabric of space-time itself would have trembled with each event. The gravitational waves produced by monopole catalysis would have a very distinct character. They would not form a smooth, continuous hum like those from inflation. Instead, they would contribute to a stochastic background with a signature leaning toward higher frequencies, a crackling static of tiny bangs. The pattern might also show specific statistical correlations, reflecting the random walk of the monopoles through the early universe. Detecting such a fingerprint would be a double discovery. It would confirm the existence of magnetic monopoles, a particle that has eluded physicists for a century, solving a deep puzzle in particle physics. Simultaneously, it would reveal that these elusive objects played an active, destructive role in shaping the thermal history of the cosmos, their deadly trails of proton decay leaving an imprint not just in missing matter, but in the very vibrations of space-time. The gravitational waves would tell us that inflation did not just hide the monopoles, it left behind a ghostly few that sang a song of annihilation as they wandered the newborn universe. The universe's birth may have been lopsided. Most models of inflation treat it as a perfectly symmetrical expansion, a uniform stretching in all directions like a balloon being inflated. But nature rarely favors perfect symmetry. Asymmetric inflation models propose that the universe's explosive growth was fundamentally uneven. In these scenarios, the inflattened field, the engine of inflation, does not roll uniformly down its energy hill. It might have a preferred direction in its internal field space, or the expansion itself could proceed at different rates along different spatial axes. Imagine stretching a piece of taffy but pulling harder in one direction than the others. The material elongates and distorts in a specific, imbalanced way. The early universe could have undergone a similar anisotropic stretch. This directional preference is not a minor detail. It leaves a permanent scar on the cosmos. The asymmetry imprints itself on everything shaped by that epoch, most notably on the primordial gravitational waves. A uniform, isotropic inflation would produce gravitational waves with a statistically random polarization pattern. But if space was stretched more along one axis, the gravitational waves generated during that process would carry a memory of that distortion. Their polarization would show a subtle but detectable statistical preference. They would not stretch and squeeze space with perfect randomness. Their patterns would lean ever so slightly in a specific cosmic direction. This is like finding a fingerprint on the cosmic drumhead, a swirl in the vibration that tells us the drum was struck at an angle. Detecting such a polarized signal in the gravitational wave background would be a direct window into the geometry of the inflationary landscape itself. It would reveal that the field-driving creation had a complex directional topography, and that our universe's expansion was a tilted, uneven sprint into existence. This asymmetry could even link to other cosmic puzzles, like the mysterious alignment of certain large-scale structures or the elusive axis of evil in the cosmic microwave background. A lopsided beginning might explain a universe that is not quite as isotropic as we once assumed. That lopsided stretch of space-time pushes our theories to the very edge of comprehension, but there is a deeper, more fundamental boundary we have yet to cross. The final theory forces us to stare into the abyss of the unknowable, a problem so profound it is known as the trans-Planckian conundrum. To understand it, we must return to the moment of inflation's birth. The quantum fluctuations that were stretched to become galaxies and gravitational waves did not appear from nothing. They existed as tiny, vibrating modes, waves in the quantum fields with specific wavelengths. Inflation, by stretching space itself, stretched these wavelengths from the microscopic to the cosmic. But here lies the crisis. For the entire observable universe to have emerged from a single, causally connected patch, inflation must have stretched these modes from lengths far, far smaller than the Planck length. This is the scale where quantum gravity reigns, where space-time dissolves into foam, and our known laws of physics completely break down. We are tracing our cosmic ancestry back to a regime where words like wavelength and particle may have no meaning. It is a conundrum because we are using the trustworthy physics of quantum field theory, which works on scales larger than the Planck length, to describe the fate of modes that originated in a realm where that theory is invalid. It is like writing a detailed biography of someone's life, starting from the precise moment of their conception, using only the laws of chemistry that govern adult biology. The starting conditions are fundamentally unknown. So how do we proceed? Theorists propose that the true nature of quantum gravity at the Planck scale must have left an imprint on these modes as they crossed the boundary from the trans-Planckian realm into the domain where our physics applies. The transition would not have been clean or silent. Different models of quantum space-time predict different effects. One idea is that the fundamental discreteness of space, a pixelated reality, would act like a subtle lattice. As a quantum wave passes from this pixelated grid into the smooth continuum, its properties could be altered, much like light changes when passing from air into water. It might experience a slight shift in frequency or phase. Another possibility involves a fundamental cutoff, a minimum allowable wavelength in nature. This would mean the very concept of a mode smaller than the Planck length is forbidden. The vacuum fluctuations that feed inflation would then have a different character from the very start, changing the initial conditions for the entire cosmic symphony. The most exciting prospect is that these trans-Planckian signatures are not erased by inflation. Instead, they are amplified and stretched across the sky. The subtle distortions imprinted on the modes as they were born in the quantum gravity realm would be magnified into detectable anomalies in the gravitational wave spectrum we hope to observe. We might find unexpected oscillations in the spectrum, a specific pattern of correlations between different frequencies, or a sharp cutoff at very high frequencies that points to a fundamental graininess of space. Detecting such a fingerprint would be the ultimate breakthrough. It would not just tell us about the physics of inflation, but would provide direct, observational clues about the nature of quantum space-time itself. The gravitational waves would carry a message from a domain forever inaccessible to any particle collider, a first-hand report from the frontier where space and time are born. The faintest whispers from the dawn of time could thus become our most powerful telescope, peering not across space but into the very fabric of reality, to witness the moment our classical universe crystallized from quantum chaos. This tapestry of 30 theories reveals a cosmos born not in a single way, but through a symphony of possibilities. From the inflationary sprint to the cosmic bounce, from colliding brains to evaporating black holes, each idea offers a unique window into that first, unfathomable instant. They paint a picture of a beginning that was chaotic, elegant, violent, or cyclic, a genesis woven from quantum foam, spectator fields, and hidden dimensions. Yet for all their stunning diversity, these stories converge on a single, profound hope: the detection of primordial gravitational waves. Those faint ripples are the one true time capsule, a direct recording of the universe's first vibrations. Catching them would be like recovering the lost opening chord of creation's symphony. It would transform our wildest speculations into testable science, allowing us to ask the cosmos directly which of these 30 keys fits the lock of our origin. The hunt is already accelerating. Across the planet and in plans for space, a new generation of ears is straining to listen. Space-based laser interferometers will scan for high-frequency hums, while next-generation telescopes will scour the cosmic microwave background for the twisted polarization patterns these waves imprint. These experiments are not just machines, they are time machines built to decode a message sent over 13 billion years ago. So stay curious. The next great discovery in physics might not come from a collider underground, but from a whisper in the void. The universe's first story is still echoing all around us, waiting for the moment we finally learn how to hear it.